Hi friends, welcome back to new session. In the last session we started construction of DC machine in DC machines chapter, and in the last session if you observe we discussed about magnetic frame or yoke, and we discussed about field magnet. See, in that field magnet also we are having a pole core, pole shoe and field winding. Three things are related to field magnet. I think we explained a pole core and pole shoe. In this session I am just going to start this field winding, whatever that remaining portion in the field magnet, that field winding I will discuss, and at the same time armature core and about commutator we will discuss in this video. See, what was the conclusion in the previous video? Please try to recollect once. I think I told regarding yoke. So yoke provides return path for the flux, and I told one more thing also. Yoke carries 50% of average value of flux per pole. And if you see pole core, and one more thing regarding yoke, I told one more thing. Yoke for yoke there is no need to provide lamination because it carries DC flux. And if you see pole core also there is no need to provide lamination because pole core also carries a DC supply. Whereas pole shoe need to be laminated to reduce eddy current losses because pole shoe is nearer to armature core. In armature core, we know already in armature core we are having some slots. In that slots only we are placing armature winding. Armature winding carries AC supply. Since pole shoe is nearer to armature core, so there are chances of having eddy current losses. So to reduce eddy current losses, we have to provide laminations for pole shoe. And I told pole shoe also, I told one more thing. Always we have to use non-chamfered poles, thereby distribution of flux waveform will get a flat top and trapezoidal, so that average value of flux per pole increases, thereby EMF increases, torque increases. Okay, and I told one more thing also. Pole arc by pole pitch is equals to, I told 0.7 to 0.8, there is a value. Okay, and see guys, in this session let me proceed with the field winding. So this field winding also, just see here I told you, if you take this one field magnet, in this field magnet only, to be frank, it is nothing but electromagnet. It is nothing but electromagnet. Okay, since it is electromagnet, we need winding through which if we send current, then poles will be created. Okay, suppose if I use permanent magnet, there is no need of using field winding. Is it clear? So definitely if I use permanent magnet, automatically flux will come. Okay, here I am using electromagnets, so obviously on that magnet you have to place field winding, and then you have to give DC supply for the field winding, then only poles will be produced. Okay, so see guys, here regarding this field winding, so generally field winding will be having connection with the armature winding. If you see in DC machine, field winding will be having connection with the armature winding. Okay, and tell me what is the value of if you want me to ask you what is the value of series field winding resistance, what is the value of shunt field winding resistance, what is the relation between the series field winding turns and the shunt field winding turns, all those things can be explained here. See, it's very simple. Generally field winding means what here? Field winding, if you want me to write MMF for the field winding, MMF, number of turns into current is MMF for field winding. Okay, FF is equals to NF into IF is the formula for field winding MMF. Okay, suppose if you take a series machine, you know guys, in series machine you can take series generator or series motor. Okay, in series machine field winding will be connected in series with the armature winding. That's the reason why we can call field winding as a series field winding. Okay, so since it is in series the armature winding, what current flowing to armature winding is more, so obviously current is high if a field winding is connected in series with the armature winding. Whenever current is more, tell me guys, cross sectional area for the field winding will be also more. Whenever current increases, definitely cross section area required for the field winding also increases. That everybody knows that. Okay, and see guys, here for the same MMF, if current is more, so what about number of turns should be less? Okay, whenever number of turns are less, so length will be less. You know formula R equals rho L by A. So I told already, whenever field winding is connected in series the armature, so it carries some more current, so obviously cross section area for that field winding will be more. And if you see length also is less, I said, so obviously resistance value will be less, so that value will be around 1 ohm. What is the conclusion? So if I use field winding in series machine, maybe series generator or series motor, okay, what is the resistance for that resistance of that field winding, I'm saying. So this RSC means what? So RSC is nothing but the resistance of series field winding, okay, that value will be very less, around 1 ohm, I can say 1 ohm, okay. So now tell me guys, so here RSC value is very less and number of turns also very less. That's why if you observe clearly, whenever I will show series field winding, we will be showing less number of turns there. This is the reason, okay. And series field winding resistance also will be very less, around 1 ohm, okay. And let me discuss if a field winding is connected in parallel or in shunt with the armature. Okay, if I connect in parallel with the armature, obviously, so if I connect in parallel with the armature, that the entire voltage whatever appears across armature, that will be appearing across a field winding. So nothing but voltage is high. So thereby number of turns also will be more. What is the relation? Voltage directly proportional number of turns. Whenever voltage is more, number of turns also more. Okay, number of turns also more. And for the same MMF, if number of turns are more, what about field current will be less? Whenever field current is less, okay, so what about cross section area required for that shunt field winding, I'm asking. That means field winding which is connected in shunt with armature. So what is the cross section area for that shunt field winding? It is less because IF is less. And see guys, whenever number of turns are more, obviously length also increases, no? So length increases, area reduces. So what will happen? Resistance value increases. Therefore shunt field winding resistance value will be more, around 100 to 200 ohms. Okay. So please try to relate these two things. Series field winding, shunt field winding. If you observe this series field winding and shunt field winding resistance value is more than series field winding resistance. Let me write here. RSH value is more than RSC. This is one conclusion. Okay. Next, let me compare number of turns. For series field winding, number of turns are less. For shunt field winding, number of turns are more. So let me write, number of turns for shunt field winding is more than number of turns for series field winding. Okay. And let me compare guys. Suppose NSH, ISH and NSC, ISA I am comparing. That means what is the, if you want to compare MMFs of shunt field winding, series field winding, so obviously shunt field winding MMF will be more than series field winding MMF. Before that, here one thing I want to compare. What is that? So let me compare shunt current and series current. Here shunt current I said it is less. Series field winding current I said what here more. That means ISH is less than ISC. Okay. You may get one doubt here. Sir, you said here IS is less than ISC. Therefore, definitely NSS IS should be less than NSC IS, like that you will think. Not correct. Because MMF always depends on, no doubt it depends on current and number of turns, but mainly it depends on number of turns. So already you know NSH is more than NSC. Though ISH is less than ISC, since NSH is more than NSC, therefore NSH ISH is more than NSC ISC. So please try to remember these relations, guys. So if you compare shunt field winding and series field winding, shunt field winding resistance is more than series field winding resistance. Shunt field number of turns are more than series field number of turns. Shunt field current is less than series field current. Shunt field winding MMF is more than series field winding MMF. So please try to remember this these things. It will be useful for us in future. Okay. Next, this is about field winding. Okay. Now let me discuss about armature core, guys. Armature core. It's very simple. just like a pole core provides accommodation for field winding, like that in armature core also provides accommodation for armature winding. In armature core you have to provide some slots, okay, in that slots you have to place armature winding, okay. So that means indirectly armature winding accommodate the armature core, accommodate the armature winding, and it offers low reluctance for the magnetic flux. That is very important. Please guys, see, if you see here, this diagram I already drawn in the previous video. So I just drawn here a very big diagram. So I think you did not, I just erased here, but it will be there in your notes. There is no need to draw once again. If you want, you can draw, okay. See guys, here whatever the flux coming from this under one pole. So pi means what generally? Here I already taken, suppose flux per pole, average value of flux per pole I had taken pi. Suppose under northward is pi. So I told already this pi is dividing like, see, always flux line starts from north pole surface, it reaches south pole surface like this. This is going like this portion. Okay, it is dividing as pi by 2, and once again from this north pole it is coming and reaches south pole surface, it is taking path like this. Once again pi by 2. It's like that. If you see from this north pole also, it is going like this and like this. It is dividing pi by 2, pi by 2. So whatever the average value of flux per pole, it is there. For that flux, this armature core provides low reluctance. Thereby, a flux will be thereby distribution of flux will be more. Okay. So armature core provides low reluctance path for the magnetic flux. That you have to remember. And one more thing, guys. See, regarding slots, we already discussed in induction machine. If you try to see that, there I told difference between open slots, semi-open slots and closed slots. Please try to refer induction machine chapter. There I told some specifications for open slots, semi-open slots and closed slots also. In DC machine, open slots are used. Why? For easily placing of winding. In this armature core, you have to provide some slots. In that slots only you are placing your armature winding. So for easily placing of winding, open slots are used here. And one more reason is there for why I am using open slots here. Open slots are used in DC machine for improving commutation. This one I wrote here. Open slots are used for easily placing of winding, and it is used for improving commutation. Okay, about this commutation, all those things it will come in future. We'll see afterwards. Okay. Next, see guys, in the previous video, if you observe clearly, I told one point. What is that? Suppose average value of flux per pole, if it is pi, I told yoke, each portion of yoke carries 50% of average value of flux per pole, like that I told. Like that, guys. See, if you want, you can see here. See, under this north pole, I am having two lines, two flux lines are there. That means that two flux lines only, I am assuming it as pi. Therefore, because of that, here yoke means only one single line is there in this portion. So that becomes what? If it is pi, it becomes pi by 2. That's the reason why I told yoke carries only 50% of average value of flux per pole. Is it clear? Now see guys, like that, if you see armature core also, here I am having only one line. See, one line only. Here also one line. Here also one line. Here also one line. But under north pole, here I have two lines. Whatever the two lines under poles, under north pole, south pole, all those things, that indicates pi. Average value of flux per pole. But if you see portion of yoke carries only 50% of average value of flux per pole, like that. Here also this 50% of flux means what? From this north pole it is coming like this. Yeah, it is dividing as pi by 2. Yes, this pi by 2 only I wrote here once again. Okay, and from this north pole it is dividing as once again pi by 2. This pi by 2 only I wrote here. Like this from this north pole, yes, here pi total flux is pi. It is dividing as pi by 2. This pi by 2 only I wrote here. And once again from this north pole it is dividing as pi by 2. This pi by 2 only I just wrote here. If you observe clearly guys, just like yoke, armature core also carries 50% of average value of flux per pole. That all I just wrote here. Armature core carries 50% of average value of flux per pole. Pi average per pole. Pi average per pole means average value of flux per pole. Okay, this is about armature core. Okay, see guys, next regarding commutator. regarding commutator. So I think in first two videos, nothing but simple loop diagram of a DC generator and simple loop diagram of DC motor, we explained what is the function of commutator. Commutator, nothing but what group of commutator segments can be called as commutator. Okay, so split rings can also be called as commutator segments. Group of commutator segments can be called as commutator. If you see in a DC generator, guys, commutator acts as what? Mechanical rotating rectifier. There is no need to repeat once again. This is already clearly given in lecture number 1, simple loop diagram of DC generator. So because commutator converts, okay, whatever AC induced in the armature winding to DC, and that DC is given to load. That's why I told in DC generator, commutator acts as mechanically rotating rectifier. And if you see in second lecture also, simple loop diagram of DC motor, I clearly explained, if you give DC supply to the DC motor, commutator converts the DC supply to AC, and that AC is given to armature winding. Therefore, commutator acts as mechanically rotating inverter. So please try to remember this one. Commutator acts as mechanical rotating inverter in a DC motor. In addition to these two, guys, commutator is having one more function. What is that? If you see in a DC machine, not only in DC machine, in any rotating machine, guys, if you want to produce torque, we need two fluxes. Okay, and relative speed between two fluxes should be equal to what here? Relative speed between two fluxes equal to 0. Is it clear what I am saying? That means with two fluxes also, two MMFs also has to rotate with the same speed. So for production of torque, we need two fluxes. Okay, there should not be any relative speed between I am saying two fluxes. Those two fluxes should rotate with the same speed. Okay, and one more third point is very important. There should be some relative displacement angle between two fluxes. That anyway we will discuss in future. If you see in already in induction machine also I discussed the production of torque. If you observe that also, that is enough. Okay, see, that means for production of torque we need two fluxes, and relative speed between two fluxes should be equal to what? 0. See, guys, in a DC machine we are placing field winding at the stator, which is stationary. That means what is the stator field MMF? I mean, what is the speed of stator field MMF? Stator field MMF speed I am saying 0. For that, rotor field MMF also should be equal to what? 0. Then only torque will produce. Is it clear? So speed should be same. Speed of stator MMF and rotor MMF should be same. Then no torque will produce. So here commutator makes rotor MMF stationary with respect to stator MMF. That means suppose in DC machine, in this case generally stator MMF is not, what is the speed of stator MMF here? 0. And commutator makes rotor MMF also, speed of rotor MMF also 0. So then only torque will produce. Therefore commutator makes rotor MMF stationary with respect to stator MMF. Suppose if stator MMF rotates with 500 rpm, rotor MMF also rotates with 500 rpm. If stator MMF rotates with 1000 rpm, rotor MMF also rotates with 1000 rpm. That function was carried out by this commutator. It makes rotor MMF stationary with respect to stator MMF. If this speed is 0, it makes rotor MMF speed also 0. If this speed is 1000 rpm, it makes rotor MMF speed also 1000 rpm. If this speed is 500 rpm, it makes rotor MMF speed also 500 rpm. It makes rotor MMF stationary with respect to stator MMF. Okay. Next, in addition to these points, guys, you should remember some more points here. See, generally, let me take this one as a commutator, commutator segments. Generally, if you observe in a simple loop diagram, I just drawn like this. If you observe clearly, if I take a coil like this, see, this is nothing but a coil. This is nothing but conductor. AB is a conductor I had taken here. AB is a conductor I had taken. CD is a conductor. Okay, and if you observe clearly, I just drawn like this. If you observe first lecture and second lecture, I just drawn like this, right? Please try to recollect. I just drawn like this. Okay, X, Y. X and Y. Okay, see guys, here this is nothing but commutator nothing but see the X segment, Y segment separated by mica insulation, I had taken here only two segments. Like a group of commutator segments can be called as commutator. Is it clear? So guys, this is the front view of this your commutator segment. Suppose if you draw like this, if you draw this commutator segments this is only front view only. Okay, so if you draw commutator segments clearly, see this is segment number X and Y I had taken, no? Like this here, so many segments will be there. Segment number 1, 2, 3, 4 and so on. Group of commutator segments can be called as commutator. So these segments are separated by mica insulation. This I can commutator segments. This is commutator segment. Commutator segments made up of hard drawn copper. It is why copper segments are made up of hard drawn copper means to reduce wear and tear. I already told guys, in a DC machine brushes are stationary, they won't rotate. But your split rings, or I can say commutator will be rotating. Okay, rotating. Therefore, there will be some friction between commutator segments and the brushes. To reduce that wear and tear, segments should be made up of what? Hard drawn copper, so that wear and tear can be reduced. And here guys, this is about mica insulation. So here it is 6 mm to 8 mm. It can withstand 30 volts to 40 volts. Okay, and let me explain this relation, guys. See, if you see here like this, in segment 1 I will be placing one connector here. In segment another segment I will be placing one more connector like this. See, I had taken only here two conductors. Only one coil only I had taken. Like this, so many coils will be there. See, example, see, this one coil and this is another coil and another coil like this. So many coils will be there. Okay. So if you see guys, in this segment, how many coils are there? How many coil sides are there? See guys, first of all, there should be you should know difference between coil sides and coil. See, it is a coil. Okay. But this is nothing but coil side. This is about coil side. Okay, so two coil sides gives you one coil here. Two coil sides gives you one coil. It is a coil side. Please try to refer synchronous machine terms belongs to armature winding. There I clearly explained about a coil side, a turn, single turn coil, 2 turn coil, n turn coil, like that I clearly explained. Please try to refer synchronous machine topic and nothing but terms belongs to armature winding. Okay, right. Here see, like this, if you see here, I told this is nothing but one side. Suppose in this segment, you see this one side, this another side. Two coil sides are there. If you observe this one also, one side, another side. So in one segment, two coil sides are there. See, in one segment, two coil sides are there. Suppose if n commutator segments, see, 1 becomes 2, right? That means double. N commutator segments becomes 2n coil sides. So I told you already, number of coils is equals to, okay, number of coil sides is equals to number of coil sides, or number of coils is equals to number of coil sides by 2. See, if you want, you can check here. Here two coil sides are there, one coil is there. Number of coils is 2 by 2 equal to 1. How many coils are there? One coil is there. Therefore, for in one segment, you are having 2 coil sides. For n commutator segments, you will be having 2n coil sides. 2n coil sides means what? By 2 means what? It becomes coils. See, coil sides if you want. See, I told n commutator segments equals to 2n coil sides. 2n coil sides means how many number of coils? So 2n by 2, n coils. There is no need to confuse. See, one coil means 2 coil sides. See, n coil means 2n coil sides. Correct or no? Therefore, n commutator segments equals to 2n coil sides is equal to 2n by 2 n coils. Okay. So, number of commutator segments is equals to number of coils. This is very, very important relation you should remember, guys. Number of commutator segments is equal to number of coils. Don't confuse with the coil sides and coil. Is it clear? Number of coils is equals to number of coil sides by 2. Always number of coil sides will be more. Example, see, in this case, 2 coil sides, 1 coil. 2 coil sides, 1 coil. That means number of coils is equals to number of coil sides by 2. In this example, I am having 2 coil sides, 2 by 2, 1. This is 1 coil. Like that, if you are having 2n coil sides, if you divide with the 2, that becomes the number of coils. So n commutator segments, n coils. Number of commutator segments equals to number of coils is the relation. Okay. Please try to remember this relation. It is also important. Okay. Right. Next, guys, in the next video, guys, we will be discussing about brushes which are placed on the split rings or commutator segments, and we'll discuss about armature winding also. Okay. Thank you.